Welcome back to the Element Explorer. In part 1, we discussed quarks in detail. If you haven't watched it yet, I've included the link in the description, be sure to check it out. In this video, we're going to dive into the fascinating world of leptons. Leptons are one of the fundamental particles in the universe, just like quarks. They are not made up of smaller particles. Leptons are a key part of the standard model of particle physics, and they come in 6 types, or flavors. Leptons are categorized into 3 generations based on their mass and the types of neutrinos associated with them. Each generation consists of 1 charged lepton and 1 neutrino. Let us know the differences between the particles and their corresponding neutrinos. The leptons like electron, muon, tau, interact with light and have significant mass, while their corresponding neutrinos like electron neutrino, muon neutrino, tau neutrino, are neutral, nearly massless, and only interact through the weak nuclear force. Leptons and their neutrinos come from some amazing places in the universe. Electrons are found in atoms, and they're also made during radioactive decay. Muons are created when cosmic rays hit the Earth's atmosphere, making high-energy particles. Taus are formed in powerful events, like when particles collide in accelerators. Electron neutrinos are tiny particles released during nuclear reactions in stars and also during radioactive decay on Earth. Muon neutrinos are made when muons decay, which happens often in cosmic ray events. And finally, tau neutrinos form when tau particles decay in high-energy processes. These fundamental particles were discovered over many years through groundbreaking experiments. Let's explore these discoveries in the order they happened. First, the electron. Discovered in 1897 by J. Thomson during his cathode ray tube experiment, the electron was the first known lepton. Next came the muon. In 1936, cosmic ray experiments led by Carl D. Anderson and Seth Neddermeyer revealed this particle, similar to the electron but much heavier. The electron neutrino was proposed by Wolfgang Pauli in 1930, but it wasn't until 1956 that Clyde Cowan and Frederick Raynes detected it in their neutrino experiment and confirmed its existence. The muon neutrino was discovered in 1962 by a team led by Leon Lederman at the Nevis laboratory, through a neutrino experiment that detected muon neutrinos produced in interactions. The tau lepton was discovered in 1975 by a team led by Martin Perl at SLAC, through high-energy particle collisions that revealed the tau lepton. The tau neutrino was confirmed in 2000 by a team at Fermilab through the donut experiment, which detected tau neutrinos produced in high-energy neutrino interactions after years of searching for this elusive particle. Leptons also have their corresponding antiparticles, called antileptons. Each lepton has an associated antilepton. Here is the list. So, what are leptons and antileptons? Leptons are fundamental particles like electrons, muons, and neutrinos. Antileptons are the corresponding antiparticles of leptons. For example, electron has an antielectron called positron, muon has an antimuon, neutrinos have their corresponding antineutrinos. So how do these antileptons are formed? Antileptons are usually created in high-energy environments, such as particle accelerators, cosmic rays, radioactive decay. So, what is the difference between leptons and antileptons? The difference lies in their charge and lepton number. Leptons, like electrons, have a negative charge, while antileptons, like positrons, have a positive charge. Leptons have a lepton number of +1, and antileptons have a lepton number of -1. This number is a quantum property that helps differentiate between leptons and antileptons. Do leptons and antileptons bond together? When a lepton and its antilepton meet, they undergo a process called annihilation. During annihilation, they destroy each other and release energy, usually in the form of photons, light. Energy. The energy from annihilation can sometimes produce additional particles, like protons and neutrons, depending on the amount of energy involved. Leptons are fundamental particles with some fascinating properties. Let's explore their key characteristics. Leptons are fermions, meaning they have a half-integer spin of 1/2. Charged leptons, like the electron, muon, and tau, carry a charge of -1, while neutrinos, the neutral leptons, have zero charge. Leptons vary in mass. The electron is the lightest, followed by the muon and tau, which are much heavier. Neutrinos, however, have incredibly tiny masses. Leptons carry a lepton number of +1, while their antiparticles have a lepton number of -1. The total lepton number is always conserved in particle interactions. There are 3 distinct flavors, or families, of leptons: the electron family, the muon family, and the tau family, each containing a particle and its corresponding neutrino. Leptons interact via the weak force and, if charged, the electromagnetic force. However, they do not interact via the strong force, and gravity affects all leptons. Every lepton has an antiparticle counterpart, such as the electron's antiparticle, the positron, and similarly for the muon, tau, and neutrinos. The electron is stable, but the muon and tau are unstable, decaying into lighter particles over time. Leptons can gain energy in interactions, leading to various forms of motion and transformation in particle physics. Leptons play a vital role in processes like beta decay and other weak interactions, which are crucial in the behavior of atomic nuclei. Until now, we have learned about fermions, including quarks and leptons. Now, let's learn about bosons, including gauge bosons and scalar bosons. Let us know important point that bosons can be either elementary particles or composite particles. Elementary bosons are particles that are not made up of smaller particles, like the Higgs boson. However, composite bosons are made up of smaller particles, called fermions. For example, mesons, such as pions, are composite bosons because they are made up of a quark and an antiquark. Even though mesons are not elementary particles, because they are made of smaller parts, they are still considered bosons because they have an integer spin, a property that classifies them as bosons. So, the key point is that some bosons are made of other particles, but they are still classified as bosons based on their spin. Bosons are a category of fundamental particles that follow Bose-Einstein statistics, named after physicist Satyendra Nath Bose and Albert Einstein. They have integer spin values, 0, 1, 2, etc., while fermions have half-integer spin. Gauge bosons include photon, W and Z bosons, gluons. Graviton is a hypothetical force. These bosons act as force carriers, mediating the fundamental interactions between particles. There are 4 fundamental forces in nature: electromagnetic force, strong nuclear force, weak nuclear force, and gravitational force. These forces are believed to have been formed during the Big Bang, and the corresponding particles like bosons are responsible for carrying and transmitting these forces. Here's a more detailed summary of the mediating particles and their corresponding forces. Photon mediates the electromagnetic force. This force governs interactions between electrically charged particles and is responsible for phenomena such as light, magnetism, and electrical interactions. It enables the transmission of electromagnetic waves, including visible light. W and Z bosons mediate the weak nuclear force. This force is responsible for processes like radioactive decay and particle transformations. It governs interactions that change the type of particles, such as the decay of a neutron into a proton, electron, and neutrino. It also plays a key role in nuclear fusion inside stars. Gluon mediates the strong nuclear force. This force holds quarks together inside protons and neutrons, forming the nuclei of atoms. The strong force also binds protons and neutrons together inside atomic nuclei, which is crucial for the stability of matter. Graviton, hypothetical, would mediate the gravitational force. While gravity is described by Einstein's theory of general relativity as the curvature of spacetime, the graviton is a theoretical particle proposed to explain gravity in quantum mechanics. It has not been observed, and there is no experimental evidence for its existence yet. Let's take a look at the properties of bosons. Photon. The photon is massless, meaning it has no mass. It is electrically neutral with no charge and has a spin of 1. The photon does not carry color charge, meaning it doesn't interact via the strong force. It's the force carrier for electromagnetism. Gluon, like photons, are massless. They're also electrically neutral. With a spin of 1, gluons carry color charge. They mediate the strong force, holding quarks together within protons, neutrons, and other hadrons. W and W bosons. The W bosons are massive, with a mass of around 80.4 gigaelectron-volts per speed of light squared. The W carries a positive electric charge, while the W carries a negative charge. Like the photon and gluon, the W bosons have a spin of 1, but they do not carry color charge. They are responsible for mediating the weak force. Z boson. The Z boson is massive, with a mass of about 91.2 gigaelectron-volts per speed of light squared. It is electrically neutral and has a spin of 1. Like the W bosons, the Z boson does not carry color charge and is involved in the weak interaction. So what is color charge? Let's break down the entire concept of color charge and how quarks interact with gluons, and I'll explain it in a way that's easy to understand. In a theory called quantum chromodynamics, quarks, the tiny particles that make up protons and neutrons, have a property called color charge. Now, don't be confused by the word color. It's not about the actual colors you see in the world. It's just a label to help scientists understand how quarks interact with each other. There are 3 types of color charges: red, green, and blue. These names are used to simplify the concept of how quarks interact through the strong force. Imagine 3 friends working together on a project. One is good at red tasks, one at green tasks, and one at blue tasks. The project is best when they each do their special task. But if all 3 try to do the same task, the project won't work. It's the same with quarks. They need to have different colors, red, green, blue, to stick together and form something stable. If they all have the same color, they can't work properly. 3. How do quarks interact? Just like electric charges can attract or repel each other through the electromagnetic force, positive attracts negative. For example, quarks with different color charges attract each other through the strong force. This is how quarks stay bound together inside protons and neutrons. For example, Z-notation spot. A red quark will attract a green quark and a blue quark. Z-notation spot. These interactions between quarks happen through particles called gluons. Gluons are the mediators of the strong force, just like photons are the mediators of the electromagnetic force. Bose-Einstein statistics is a set of rules used to describe the behavior of bosons, particles with integer spin. Unlike fermions, which follow the Pauli exclusion principle and cannot occupy the same quantum state, bosons can occupy the same state at the same time. This property leads to unique phenomena, such as Bose-Einstein condensation, where, at extremely low temperatures, a group of bosons condenses into the same ground state and behaves like a single superparticle. For example, laser pointers. When you use a laser pointer, all the light particles, photons, are in the same quantum state and travel in the same direction, creating a focused beam of light. This behavior is similar to what happens in Bose-Einstein condensation, where particles group together and exhibit collective properties. Let us discuss about scalar bosons. They are mass carriers that play an essential role in our understanding of particle physics, helping to explain the origin of mass in the universe. They have zero spin, meaning they don't have any twisting motion. In simple terms, it's like a particle that doesn't rotate or spin around itself. The Higgs boson is the most famous scalar boson. It was discovered by scientists at CERN in 2012. The discovery was made using the Large Hadron Collider, a huge particle accelerator. The Higgs boson was first predicted by Peter Higgs and François Englert in 1964. They came up with the idea that this particle was needed to explain why some particles have mass. The scientists at CERN found the Higgs boson after many years of experiments, and this discovery proved that their theory was correct. Properties of scalar bosons include zero spin. Scalar bosons have zero intrinsic angular momentum. This property means they do not rotate or possess any spin-related effects. Parity. Scalar bosons have even parity, meaning their properties remain unchanged when the spatial coordinates are inverted when the system is reflected in a mirror. Mass. Scalar bosons can either be massless or massive. For example, the Higgs boson is a massive scalar boson. A massless scalar boson would have different characteristics and interactions than a massive one. Role and force mediation. Scalar bosons can mediate forces or interactions. The Higgs boson is a famous example, which is responsible for giving other elementary particles their mass via the Higgs mechanism in the Standard Model of particle physics. Symmetry properties. Scalar bosons are invariant under Lorentz transformations, meaning their properties do not change when they are subjected to rotations or boosts in spacetime. Interaction with matter. As force carriers, scalar bosons can interact with other particles, but they are not affected by the same interactions as particles with spin, such as fermions. The Standard Model of particle physics explains three forces: electromagnetic, weak, and strong forces, using tiny particles called bosons. But it doesn't include gravity. That's because gravity is different from these forces. It is described by Einstein's theory of general relativity, which works on a much bigger scale, like planets and stars, not the tiny scale of particles. While scientists believe that gravity might also be carried by a particle called the graviton, we haven't discovered it yet. The problem is that gravity works in a way that doesn't fit with the quantum world that the Standard Model describes. Right now, scientists are trying to come up with a theory that can explain both gravity and the other forces in one unified way, but it's still a big challenge. We have discussed all the elementary particles. If you haven't watched part 1 of this video, please check it out, and don't forget to subscribe to the Element Explorer for more amazing content.